Lightning is an example of an electrostatic discharge. What's happening in lightning? You can also feel a small little, we could say, lightning bolt, in other words, electrostatic discharge, if you rub your feet against a carpet, if you live in a very dry area, and then you touch something like maybe your friend or maybe a door handle, and then you feel a shock. You might even see a little spark, especially if the light is off. And you might hear a crackle. That's also a discharge. What's happening in electrostatic discharge? To understand that, let's first understand what charged state means. Charged state might be neutral or charged. If it's charged, it might be positive or negative. Within positive and negative charged states, we can get degrees of how charged the object is. It might be only slightly positively charged or very positively charged, slightly negatively charged or very negatively charged. And obviously there aren't just two categories, slight and very charged. You get many degrees in between of how charged it is, the extent of the charged state. Now we need some way to measure how charged an object is. We need a unit, and the unit that scientists generally use is the coulomb. So let's try and understand what is a coulomb, how much is that. The reason why objects are charged at all is because of an imbalance between positive and negative charges. So a neutral object has just as many positive as negative charges. So if we could look at the atoms that make up the neutral substance, we would see that there are just as many protons as electrons in that substance. A negative object has more electrons than protons because it gained electrons. Electrons move to cause things to be charged. Protons do not move. And a positively charged object has fewer electrons than protons. In other words, more protons than electrons because it's lost some electrons. So depending on how many electrons something loses or gains, it's very or slightly positively or negatively charged. Now the charge of one electron is minus 1,6 times 10 to the power minus 19 coulombs. That minus does not mean less than nothing. It simply means it has a negative charge. Now this number is very, very small. Here I've written it in some different ways to give us the idea of how small this number is. An electron is itself a very tiny object. There are billions and trillions of them in all objects around us, and each electron has a very small charge according to the Coulomb unit. Now here we have a neutral object. The neutral object doesn't have any extra or fewer electrons compared to protons, and so its charge is 0 coulombs. Now let's imagine that to this neutral object we add just one electron, so that now the object is negatively charged by just having one more electron than proton. Then that object would have a charge the same as the charge of an electron, minus 1,6 times 10 to the power minus 19 coulombs. Certain values are impossible. For example, it's not possible for us to cut up an electron and transfer only half an electron to a neutral object to give it a charge of half the electron charge, in other words, this value here. That is impossible because you cannot divide electrons. And that brings us to a very important principle, the principle of charge quantization, which simply says that charge always exists in whole numbers of the electron's charge. But let's continue looking at some examples that are possible. An object might have 2 more electrons than protons. Then its charge is double that of an electron, minus 3,2 times 10 to the power minus 19 coulombs. If it has 10 more electrons than protons, well then its charge will be 10 times that of a single electron, and so on. Now if there are 6,25 times 10 to the power 18, now that is a huge number. If there are so many more electrons than protons in this object, then its charge will be that number multiplied by the charge of a single electron, which gives us 1. Well, minus 1. That minus means that it's negative. Minus 1 coulomb. So that's how much a charge of 1 coulomb or minus 1 coulomb is. It means that there are 6,25 times 10 to the power 18 more electrons than protons. And if we have double that many more electrons than protons, well then that object has a charge of minus 2 coulombs, and so on. Of course, objects can also be positively charged. If an object has only one electron fewer than its proton number, then it has a charge the same as an electron's charge, but now positive, not negative. Just as with the negative charges, there are certain positive values that are impossible due to the law of quantization of charge. If an object has 2 fewer electrons than protons, then it has a charge double that of a single electron, but positively. 10 fewer electrons than protons, its charge is 10 times that of a single electron, again positively. And again, if it has this number, fewer electrons than protons, its charge is positive 1 coulomb, and double that, positive 2 coulombs, and so on. Now, if you have two objects that have different charged states, then there is a potential difference between them. A potential difference is often called a PD, and that can cause a discharge. It might not, but it might. It depends whether there is a path for discharge to happen along or not. Now, what is discharge? First of all, why does it happen? Discharge happens to remove the difference in charge state so that the two objects are no longer different in charge state. Instead, that they have the same charge state as one another. And in the process, that also removes the potential difference between them. And in this way, it makes them more stable. So that's what drives discharge. Well, what is discharge? We've already discussed that lightning is an example of discharge, and sometimes you might get a shock, and that's an example of discharge. But what's actually happening during that discharge? Discharge is the movement of electrons. So when you see a bolt of lightning, that is lots and lots and lots of electrons moving. They'll be moving from a negative part of the cloud maybe to a positive part of another cloud or the same cloud, or maybe to the neutral Earth, so as to remove the difference in charge state between different parts of the sky and the Earth.